In this video, I will give you a high-level overview of our paper, Smoothness Adaptive Hypothesis Transfer Learning, which is to be presented at ICML. Let's begin by introducing the background of the learning problem. In this work, we consider two regression models as target and source model, where the goal is to leverage the knowledge from the sample-rich source model to enhance the learning on the sample-scarce target model. We consider the model shift setting, and we also consider the source model lies in the subloop space of order M0, while the offset between the target and the source model lies in the smoother subloop space. The hypothesis transfer learning aims to transfer knowledge from a source domain to the target domain by using the changed source model while we learn the target model. Since we are considering the non-parametric regression, the learning framework we consider in this work combines the prevalent offset transfer learning technique in the HTL and the kernel-rich regression in classical kernel methods. The learning framework consists of two phases. In the first part, we use the source data to estimate the source model, the FS hat. In the second part, we use the target data to estimate the offset by subtracting the predicted value via the FS hat to the target label. The final estimator is produced by adding the source model and the offset model. However, while this framework is popular and standard in non-parametric HTL, there are some limitations. First, the current framework is smoothness agnostic, meaning that without knowing the relative smoothness of Fs and F delta, one can typically use the same kernel regularization in both phases. This indeed against the simple offset principle that leads to the success of HTL. Recall that we assume the offset is in the smoother subloop space. That means the F delta should be much easier learned by Fs. However, using the same kernel regularization will not take this advantage. Second, the current learning framework is non-adaptive. Their rate optimality relies on knowing the true subloop smoothness M0 and M and employing the correct kernel in both phases. Therefore, this limitation indeed leads to the goal of this paper, which is to answer the following question: how to develop a HTL algorithm such that Fs and F delta can be learned adaptively and optimally with this varying subloop space. First of all, we notice that the regression problem in both phases are indeed single task KRR, meaning that we only need to find a solution that can adaptively and optimally learn the Fs and F delta separately. Therefore, we give a revisit of KRR. So for kernel K and its induced RKHS HK, the KRR estimator is given as the minimizer of the following regularized empirical risk minimization problem. And if you assume the true function lies in the subloop space, then the minimized conversion rate of this L2 error is given as follows, which is in the order of n to the minus 2m0 divided by 2m0 plus d. In classical kernel literature, it states that if the imposed RKHS HK coincides with this subloop space HM0, then the minimized rate is attainable. However, the problem emerges as how to choose a kernel K to achieve this rate without even knowing the M0. Or more exactly, how can we find out a RKHS to coincide with this subloop space? An appealing tool is to use the misspecified property of the KRR. That is, even if imposing a wrong kernel, one can still achieve the optimal rate. The following position indeed gives us a full view of what this property means. Suppose that the Ft hat is the target-only KRR estimator and K is the imposed kernel. First, if K is the Martin kernel and its induced space coincides with subloop space with order M0 prime, then we will have the conversion rate of Ft hat as the following. Specifically, if the m0 prime is greater than m0 divided by 2, then we will hit the minimax rate exactly. However, if this condition doesn't hold, that means the m0 prime is less than the m0 divided by 2, then for any choice of parameter lambda, the lower bound of ft delta will strictly larger than the minimax rate we have in the first point. That means no matter how we choose a lambda, there's no possibility that we achieve the minimax rate. And this phenomenon is called the saturation effect of the KRR. Therefore, even though there is a potential solution that by imposing misspecified Martin kernel to achieve the rate optimal HTL, there is a fatal drawback. That's one might end up choosing a less smooth kernel and never being able to obtain the minimax rate because of this saturation effect. And therefore, this drawback indeed gives us a clear demand for a kernel with a more robust misspecified property. In this section, I will show you that the design kernel is indeed the Gaussian kernel. Let me first give you some intuition of why we target on the Gaussian kernels. First, in the misspecified KRR case, we can see it's always better to use the over-smooth misspecified Martin kernel because we want the m0 prime to be greater than the m0 divided by 2. Second, we notice the fact that the Gaussian kernel is the limit of Martin kernel. That means if one employs the Gaussian kernel, one will always force in the regime of over-smoothing and never afraid of the saturation effect. Therefore, given the Gaussian kernel is a design kernel, we give the formal statement of our non-adaptive rate result by imposing the Gaussian kernel in KRR. We let the K be the imposed kernel and is a Gaussian kernel with fixed bandwidth. Then we let f hat be the KRR estimator that learns from the target dataset only. Under some certain standard assumption, if the lambda decay exponentially, then the following statement states that the f hat hit the minimax optimal rate. The key takeaway of this theorem is that one is able to obtain the minimax optimal conversion rate with fixed bandwidth Gaussian kernel. And since the Gaussian kernel smooths a lot than the Martin kernel, the lambda has to decay exponentially, while the misspecified Martin kernel only requires lambda to scale polynomially. We also compare our work to some of the existing works. Here, we assume the mean function belongs to the Sobolev space with order m0. In the paper 1 and 2, the author considered imposed RKHS as another Sobolev space with order m0 prime, and the result in the paper 1 and 2 indeed recall what we have in the misspecified KRR proposition. In the paper 3, the author also considered using the Gaussian kernel as the imposed kernel in the KRR. However, they consider the Gaussian kernel to be variable bandwidth. They state that if one have the lambda and the bandwidth to decay polynomial in N, then one can hit the minimax rate arbitrarily close but do not exactly. The author of paper 4 improved the rate in the paper 3 by having some additional assumption on the data. They assume the data have some lower intrinsic dimension. Then the estimate can hit the minimax rate exactly up to some logarithmic factor. In our work, we say that even with a fixed bandwidth Gaussian kernel, we can hit the minimax rate exactly by having the lambda to decay exponentially in N. We also would like to know that this work is motivated by the paper 1 and 2 because imposing the Gaussian kernel in the KRR is equivalent to having the m0 prime going to infinity. However, we want to know that having the m0 prime going to infinity will never make the optimal order of the lambda to be checkable, because if you plug the m0 prime as an infinity in this form, it will only tell you that the lambda should decay much faster than the polynomial, but do not tell you what exactly the form should be. However, in our work, we identify that the correct order for the lambda to decay should be exponentially. While the Gaussian kernel can help us to avoid the saturation effect and provide the ray optimality possibility, we still require knowing the M0 to tune the lambda. Therefore, in the paper, we also developed another adaptive process via the standard chaining and validation approach to create an adaptive estimator. In this process, we first construct a smoothness candidate M, and we divided the target dataset into two parts. In the first step, for each candidate in this candidate set, we create a non-adaptive estimator by using the first part of the data. And in the second step, we find out which of these non-adaptive estimator achieve the minimum empirical L2 error over the second part of the data, and we pick it as the adaptive estimator. In the following theorem, we show that the adaptive estimator construct through this standard chaining and validation method can achieve the minimax rate up to some logarithmic factor. With the result established in the target-only KRR or the single-task KRR, we can now turn into the transfer learning context. In this paper, we propose a transfer learning algorithm called the Smoothness Adaptive Hypothesis Transfer Learning, aka SATO. Since we already showed that using the Gaussian kernel can adaptively and optimally learn the true function. Therefore, what we're going to do is just like we repeat the same procedure for both fs and f delta. So in the algorithm, in the first step, we first define the smoothness candidate set for both fs and f delta. Then in the second step, we conduct a two-phase KRR based HTL, with each phases follow a standard chaining and validation we showed before. In the paper, we also provide a theoretical guarantee for the proposal algorithm SATO. We consider the parameter space as capital theta, which is parameterized by h, r, m0, and m, where the little h quantifies the similarity between the target and the source model, and the small h indicate that a high similarity between the target model and the source model. The following theorem will provide the lower bound and the upper bound for the SATO improbability. And by checking the lower bound and the upper bound, we can see the SATO achieved the optimal learning rate up to some logarithmic factor. We now dive into the upper bound of the SATO. The upper bound of the SATO consists of two terms. The first term is the rough estimation error, while the second term is the offset estimation error, which reflect the error that we estimated the fs hat and f delta hat. We can see the transfer dynamic is jointly determined by the source sample size ns and also the factor psi u. Compared to the target-only KRR learning rate, the SATO indeed produces a faster rate with a smaller psi u and a larger ns. There is indeed a phase transition happening in this procedure. With a small psi u, the first turn in the upper bound of the SATO indeed becomes the leading turn, and then with a larger ns, this part will have a much faster rate than the target-only KRR rate. We also compare our rate to existing works and show our rate provide a different interpretation for the transfer learning efficacy. In our rate, the factor that controls the phase transition is indeed psi u, which is the ratio of the signal strength of offset to the source model. While in the existing works, this factor is only identified as h squared. Our bound indeed indicate that the transfer learning efficacy via the offset transfer learning, not singly depending on the margin of this dissimilarity measure h, but generally depending on the ratio of the signal strength between the offset and the source model. Indeed, this ratio geometrically approximates the angle between the source model and the target model. To illustrate this point, in the following figure, we create two sets of source and target model that possess the same edge, while the angle between them are different. The ray in the existing work indicate that the two pairs have the same transfer learning efficacy because they have the same edge. However, the red pair indeed possess the higher similarity because they have a smaller angle and thus have a higher transfer learning efficacy. And our rate can confirm this fact because the red pair in our case will produce a smaller size U. In this paper, we also conduct the experiment to confirm our theoretical finding. Regarding to the target-only KRR, we construct the FT from the Gaussian process such that the FT have different smoothness. In each of these plots, we show the empirical and theoretical error decay curve for non-adaptive and adaptive estimator under different smoothness. And we can see that the estimated decay rate matches the theoretical rate perfectly. In terms of the transfer learning context, we manipulate the simulation setting such that the conversion rate of the estimator from settle is in the order of nt to the minus 2m divided by 2m plus 1, where the m is the smoothness of the offset. In each of these figures, we plot the generalization for the target-only estimator, settle, and the theoretical result under different m and h. And we can see the generalization error decay of the settle match the theoretical one perfectly, and it consistently outperform the target-only learning. This page gives us a summary of the contribution within this paper. In classical kernel master regime, we show that when the true function lies in the subloop space, then employing fixed bandwidth Gaussian kernel in KRR can attain the minimax optimal rate by having the lambda to decay exponentially. In transfer learning context, we present a smoothness adaptive and rate optimal hypothesis transfer learning called settle. The optimality is guaranteed by employing the Gaussian kernel to avoid the saturation effect and allow the possibility of optimality. The adaptivity is through the standard training and validation approach to achieve adaptive rate. This page concludes this video. If you are interested in more detail, please check our paper or drop me an email for discussion. Thank you.